Hello and welcome to our lesson on analyzing graphs of functions. So we're going to talk about some characteristics of graphs that we should be able to read, and these are graphs of functions. Characteristics like where is the graph increasing, decreasing, constant, where is it positive, where is it negative, what do those things mean, what are the end behaviors, where are turning points, what are points of inflection. So hopefully these are all things that are familiar, but our goal in this pre-calc class now again is to look at some of these things through the lens of calculus. And so I'm going to introduce some terminology that may be new, or just some ways of looking at these things that may be new, and maybe none of it's new, and that would be the good news, right? So first, we know that a function's inputs are considered the independent quantities, so we say x is like the independent variable, and the outputs are quantities that are dependent directly on those inputs, so we call the outputs, the y's, our dependent variable. And because of this, when we are analyzing a function, since those x values are independent, I don't want to say they're unimportant, but they're not dictating the behavior of the function. The behavior is based off of the y values. So generally, if we're analyzing some behavior of a function, we do need to account for both of the quantities, both of the variables in our situation. But the inputs, or the x's, those are generally just used as a frame of reference. Sorry, I can't speak. So what I mean is we'll use the x values to say, hey, here's the place on the graph we want to look. Now in this area, over this interval, in this domain, what's happening to our y values? How are they behaving? So the behavior that we're going to try to analyze is based on, again, the outputs. So we use our inputs as a frame of reference, again, because the inputs are independent. Like I can take all real numbers and plug into a whole variety of functions, but how they behave, or the behaviors that we're analyzing are, again, based on the outputs. What are the outputs doing? Those are the things that will vary from one function to another. So, speaking first about increasing, decreasing, or constant intervals. When we're reading these behaviors, we are reading our graphs from left to right, just like we read a book. So from left to right. Now, if we're on the x-axis, reading from left to right, what's happening to the x values is they are increasing. So we are identifying intervals that are increasing, decreasing, or constant as x increases. That's our frame of reference. So as x is increasing, what is happening to our y's? Are they increasing? What is happening to our y's? Are they decreasing? Are they constant? So if we're reading from left to right, if we're reading as x increases and the graph is moving up, that means it is increasing. So I think that's generally how, conceptually you learn about this. We say, oh, the graph is moving up from left to right. We say it's increasing, and that's still true. But to make it a little more mathematically precise, what we mean when we say as we read from left to right, the graph is going up, we mean as x increases, so does y. Y increases. Or if we're reading from left to right and the graph is moving down, that downward slope or downward movement means our graph is decreasing. But again, we want to keep in mind both quantities. So as we read it from left to right means we are following, or the x is increasing, and as when we say the graph is decreasing, we mean the y's are decreasing. So as x increases, y decreases. That would be a decreasing portion of the graph. Now, if you're reading a graph from left to right and it isn't moving up or down, meaning you have a flat piece of graph, we would say that that graph is constant. And again, to put the frame of reference in there, it means as x is increasing, y is not doing anything. It is a constant value. Now, this concept is not new and hopefully an easy concept. The only thing that can get a little tricky is how we describe where these behaviors are happening. So to describe where the behaviors are occurring, we use intervals of x values. Again, that's our frame of reference, so it makes sense to do that. So specifically, what we're doing is we're looking for the domain over which our function is increasing, or over what domain is it decreasing, or over what domain is it constant. So we want to state the domain that corresponds with each of these behaviors. So let's look at an example. If we want to identify an interval or intervals where this function is increasing, decreasing, or constant. Again, I think just reading it and identifying is pretty easy. We just got to be careful about how we state where the behaviors are occurring. So if I was reading this graph from left to right, I can see that this first section of graph is increasing until I get here, and then it takes a turn, and then we see that the graph over this next interval is decreasing until we get here. Then it takes another turn, and I can see again I have another portion of graph that is increasing until I get to that corner. And then over this interval, the graph is not moving at all, not up or down, I mean. So as x is increasing here, this thing is constant, it's flat. And then I get to that other corner and it turns again, and we see that this last portion of the graph is, let's be consistent here, nope, that's my eraser, decreasing. Okay, so if I was just, again, reading from left to right, I would say that over this interval, the graph is decreasing. Over this interval, what am I saying? Over this interval, the graph was increasing. It was going up, and then it turned and it was going down. So now my eraser's on. Goodness gracious. This little section is decreasing. Then it turned again. We had another increasing section, and then this one was flat. So this would be a constant portion of the graph. And then again over here, we see it's going down left to right. So this is decreasing. Okay, so again, not a hard concept, just to read it left to right. It's going up, it's going down, it's going up, it's flat, it's going down. Now it's giving the answers. How do we state where these behaviors are occurring? So let me just get rid of all this. You can see it all at once. So this first section that we said was increasing, okay, this increasing portion of the graph, when I want to state where that's happening, what I want to know is over what domain is that interval. So I need the x values that correspond with that interval. So if I take this down to the x-axis, I can use it as my guide. This is an x value of -1, and this graph going down forever is also going left forever. So these are the x values that correspond with that interval, the x values from -infinity to -1. So we would say this graph is increasing from -infinity to -1. And you may be wondering about the parentheses or brackets on these intervals. It's a little debatable, but I tend to use parentheses regardless. Like, I always use parentheses on this interval, because if I ask you what's happening at -1, at this point we aren't actually increasing or decreasing, so I don't think we can include that endpoint. Now again, some teachers would argue that, but I'm going to go with parentheses, okay? So that little section was increasing. We also said this section here was increasing. So that section again corresponds with what domain, from what x value to what x value is that behavior occurring. So this is an x value of 1, and I can see here this x value of 2 corresponds. That is the domain over which that interval, or which that graph is increasing. So we're going to say not only is it increasing from -infinity to -1, it is also increasing over the interval from 1 to 2. Alright, so again, those are domains. Those are intervals of x values where those behaviors are occurring. Now we said the graph was decreasing here and also decreasing here. So when I say here, what do I mean? I mean from what x value to what x value are those behaviors occurring. So this first piece that I highlighted corresponds with this interval of x values. It's the x values between those two increasing pieces. So that interval starts at -1 and stops at +1. So we're going to say it's decreasing from -1 to +1. And then the other interval here, oh, I did that, is going to start at +6. And this graph going down and going right forever means this interval is going to, of x values, is going to continue forever. So it's also going to be decreasing from 6 to +infinity. So from 6 to +infinity. And then constant, this is the one portion of graph that was constant, and I can see that interval starts at an x value of 2 and stops at an x value of 6. So this is the interval of x's that corresponds with that section of graph. So again, we would say this graph is constant over the interval from 2 to 6. So constant decreasing, and increasing. Okay, so again, not a tough concept. Just read it left to right. It's going up, it's going down, or it's flat, so it's increasing or decreasing or constant. When you're just stating where those behaviors are occurring, it is the domain over where these things are occurring. But again, all of this behavior is as x increases. So again, left to right means over the interval from -1 to negative, or negative infinity to -1, as x is increasing, the y's are increasing. So let me just follow this one more time. As x is increasing, the y's are increasing here. And then x is going to be increasing throughout, but now the y values are decreasing, and now the y values are increasing, and now the y values are flat, and now the y values are decreasing. Right? All based on that entire time, the x values increasing. Okay, so that's left to right. X values are increasing. What are the y's doing? All right, so hopefully that makes sense. Next, we're going to talk about intervals that are either positive, negative, or neither. And again, this is based on y values. So we say that a function is positive if its outputs are positive. So a function is positive where its outputs are positive. Well, where do we have positive outputs? Positive outputs, those are positive y values going to be above the x-axis. So our graph, a function is positive where its outputs are positive, which means it is where it is above the x-axis. Okay, a function is considered negative, again, where its outputs are negative. And where do we have negative outputs? Where do we have negative y values? We have those below the x-axis. And then a function is neither negative or positive if its outputs are not negative or positive. How could they be neither negative or positive? Well, that means the outputs would be 0. So where do we have outputs of 0? If our y values are outputs that are 0, we are on the x-axis, which means we are looking at an x-intercept. So we're above the x-axis, means we have positive outputs, means our graph is positive. If we're below the x-axis, means our outputs are negative, means our graph is considered, our function is considered negative. And if we are on the x-axis, we're not positive or negative, we're 0. So we're neither positive or negative. And again, this happens when we're on the x-axis, so this happens at x-intercepts. Okay? Now, just like with the intervals that are increasing, decreasing, or constant, if we want to state where these behaviors are occurring, we are going to state these using intervals of x values, since those are our frame of reference. From what x value to what x value are we positive, negative, or for what x values are we neither? So we again want to state the domain that corresponds with each of the behaviors. Okay? So let's look at an example here. Again, trying to identify where we're positive, negative, or neither. So we're going to start with the neither. That's not going to be positive. A graph or a function will not be positive or negative if the output is 0. So outputs of 0, again, would be our x-intercept. So I can see it crossing the x-axis here. I can see it touching the x-axis here. At those 2 points, our output being 0 means we're not positive or negative. So we are neither positive nor negative at 2 coordinates. Now, I'm not going to write them as coordinates here just because I don't want them to be confused with intervals, and that's what we're writing for the rest. So I'm going to say it's the set of x's such that x is equal to -1 and a +1. So let's say plus or minus 1. Those are the roots here. So that's where we're neither positive nor negative. So these would be the x-intercepts. Maybe I'll just write it both ways. At -1, 0, and +1, 0. But again, those are coordinates, okay, not to be confused with the intervals that we're going to be writing for the next couple of pieces. So it's helpful to find those roots first because they're the separators between the positive and negative portions of the graph. So when we're hitting the x-axis, again, not positive, not negative because we're 0, but anything before or after those points has to be one or the other. So again, let's just read this graph. So this section of the graph right here, even though it is decreasing, all the outputs over this section of the graph, they are positive outputs. They are above the x-axis. So this portion of the graph, we would say, is positive, right? Or we hit the x-axis here, so we're not positive or negative, but right after that intercept, I see a portion of the graph that is negative. So this happens to be decreasing, and then it happens to be increasing, but it doesn't matter when we're talking about positive versus negative. That whole section of the graph is below the x-axis. All of its outputs are negative, so that whole section of the graph is negative. And then again, it touches the x-axis, and so not positive or negative there. And then, let's see, so this piece we said was negative. So we hit the x-axis, we're not positive or negative there, but then after, we have another piece of the graph decreasing, but also negative. Now we just got to be careful again giving the answers. So I can't state this as one I cannot state this as one continuous interval, because right here at this point we don't want to include that positive one. It is not positive nor negative. So we actually need to separate this. Let me just change colors into two different. So this piece is still negative, but it has to be distinguished between or from the other interval. Okay? So positive. I highlighted that positive portion of the graph in yellow. Again, when I state where it's at, I want to know what is the domain for that piece. So this graph going up is also going to the left forever, which means left forever up to that root. Those are the x values that correspond with that section of graph. That is the domain for that section of graph. So we're going to say it's positive over the interval from negative infinity up to that root at negative 1. And I said root instead of x-intercept. Hopefully we're okay with that word. So x-intercepts, or we can call them roots. So positive, we said from negative infinity to negative 1. And then negative, we've got two intervals that are negative. We have the one interval, let's go back to green, that starts at the root here at negative 1 and then goes into the other root at positive 1. So that section of graph corresponds with that domain. So it's negative from negative 1 to, this is a root at positive 1. And then we're going to unite that with this last interval, which again technically starting at 1 but going forever. So the x value is from 1 to infinity. So from 1 to infinity. And again, we have to make sure we separate this. We keep the parentheses on the 1 to exclude the 1. If I just went from negative 1 to positive infinity and lumped the 1 in there, then that would imply that again, at 1 we are negative and we are not. At 1 we're 0. The function value is 0, and 0 does not have a sign attached. Okay? Again, hopefully making sense and feeling familiar. Alright, let's look at the next piece. We're going to describe some end behaviors. So what are end behaviors? Again, something you've seen before. They are exactly what they say they are. End behaviors describe the behaviors of the graph at its ends. So specifically the behaviors of the outputs. That is the important part. So if it's increasing, it's because the y's are increasing as x increases. If it's decreasing, it's because the y's are decreasing. If it's positive, it's because the y's are positive. If it's negative, it's because the y's are negative. So when we're looking at end behaviors, we are describing the behaviors of the outputs. What are the outputs doing at the ends of the graph? Now, when I say the ends, again, that's my point of reference. So at the very left end of the graph, that would be as x is approaching negative infinity. Or at the very right end of the graph, that would be as x is approaching positive infinity. At those ends, the left and the right ends, where is the y value? What is the y value approaching? Okay, so again, what we're trying to focus on here is as x is approaching infinity or negative infinity, that's the left and right. If we use x's as our point of reference, follow the graph left, follow the graph to the right, where the y is headed. So what is y approaching is like the question we're trying to answer with end behaviors. So we're going to try to describe the end behaviors for a few functions here. So first one, we're looking at a function called f of x. So when we state the end behaviors, again, we have to give our point of reference. What we want to know is as x approaches negative infinity, what is f of x doing? Where are the function values headed? So we use those little arrows for the word approaching. So again, as x approaches negative infinity, f of x, the outputs, approach what? And that's going to be a question that we're going to answer in just a second. But let me go ahead and get the rest of this written. So we would say as x approaches positive infinity, to give a point of reference for the other end, right? Again, as x approaches positive infinity, what is f of x approaching? What are the function values? What are the outputs approaching? So when we say x is approaching negative infinity, so if we're on the x-axis going toward negative infinity, we're going toward the left. So that is the point of reference that's saying go to the very left end of the graph and tell me where the y value is headed. So this is a way to ask you to go to the left end. If you go to the left end of this graph, on this left end, right, what is the graph doing at the same time that it's going left? It is headed down, and it's headed down forever. So if we're on the y-axis going down forever, where are the y values headed as we go down forever? Well, they're headed toward, back to blue please, toward negative infinity. So the y values are going to negative infinity. Okay? Now here, if we are looking for this as our point of or frame of reference, if x is approaching infinity, again, if we're on the x-axis and we're approaching positive infinity, we are going to the right. So this is notation to say, hey, go to the right end of the graph. That's our frame of reference. Now, if we go to the right end of this graph, we want to see where the y values are headed. Okay, so there's the right end. Well, that graph is going up forever. So if we're going up forever, where are the y values actually headed? So these y values are headed up forever toward positive infinity. So we would say, as x goes to infinity, that means on the right end, our graph also goes to positive infinity. So positive infinity. Alright, and again, hopefully this isn't new. Hopefully it's making sense and seems familiar. So let's look at the next one. Now that first one is a polynomial function. We'll talk more about those in a later topic. This maybe we're recognizing as an exponential function. So again, if I wanted to analyze the end behaviors there, I want to know first what is happening as x approaches negative infinity, and I also want to know what is happening as x approaches positive infinity. So that is on the left end and on the right end, where are the function values headed? So as x goes to negative infinity, what is g of x doing? What are the function values doing? So again, this is the left end. If I go to the left end, we see the graph headed up, and up means the y values are going up forever toward positive infinity. Now if we look at the other end, this one is a little tricky. So this one, as x goes to infinity, says go to the right end of the graph. Now when I go to the right end of the graph, this graph appears to be flattening out. And that is actually what is happening. So again, this is an exponential function. What's happening here, this graph of flattening out, means that this graph is approaching an asymptote. And this appears to be a horizontal asymptote at y equals 1. So let me write this up here. Horizontal asymptote at y equals 1. That means the farther and farther we go toward the right, so follow this arrow in green, the farther and farther we go this way, the closer and closer that function is getting to that line, which means the y values on each of those points is going to be getting closer and closer to that y value of 1. So on the left end, the graph goes up forever toward infinity, but on the right end, our function values, our y values, are going to be approaching the horizontal asymptote that has a y value of 1. So getting closer and closer and closer to 1. Okay? Alright, over here we have, hopefully you recognize, maybe you don't, maybe it's been a minute. This is a rational function, and I can see some asymptotes in here again. This looks like a vertical asymptote in here, although that one doesn't really matter because we're going to be looking at the end behaviors. There's another asymptote in here. Again, I don't know if you can see it or even if I can sketch it because I'm going to have to turn my iPad. Looks like there's an oblique or slanted asymptote in here. And those asymptotes do definitely affect our end behaviors, okay? But let me just go ahead and put the other one back in. So we have two asymptotes in this graph. It appears. Irregardless, we should be able to read our end behaviors. So again, let's look as x is approaching infinity, and let's, I think I did negative infinity first, negative infinity, and let's look as x is approaching positive infinity. So let's go to the left end of our graph first. On this left end of the graph, what's happening? Well, at the same time we're going left, the graph is headed up. Right? You can see how that graph is going to be headed up. So if we're headed up at the same time that we're going left, that means those y values continue to increase upward toward positive infinity. So we would say as x goes to negative infinity, h of x goes up toward positive infinity. So the x's are decreasing while the y's are increasing. Okay. And then on the right end of the graph over here, this right end, if we were to follow that, at the same time that we are going right or x is increasing, this graph is going to keep headed down. So if it's heading down, again, that would be down forever toward a negative infinity. So as x approaches infinity, we would say h of x approaches negative infinity. So as x's are increasing, y's are decreasing. Okay, for that branch of that rational function. And again, hopefully stuff that looks familiar. Okay, so we've got lots of behaviors down the last little piece I want to show you. Or what you should be able to identify are turning points and points of inflection. And these ones actually come up quite a bit in calculus. You start doing first derivative and second derivative tests to identify these points because the graph, the behavior of the graph changes at these points. So at a turning point, and I kind of mentioned this as I was looking at the increasing, decreasing section, at a turning point, a function does just that. It turns. Now when I say it turns, I mean it turns from increasing to decreasing or vice versa. For example, here, if I was following this graph, it is decreasing till it gets right there, and then it turns, and it is increasing. So that point where it changes from decreasing to increasing, that is called a turning point. We can also call that the vertex of that graph, so turning points are also called vertices. Now this particular one that I've highlighted here happens to be at the bottom of that graph. When we go from decreasing to increasing, then that vertex, that turning point, is referred to as a minimum. And then we have different types of minimums. We have local or relative minimums. Then we have these absolute or global minimums. We'll talk about those more later. For now, just know if you have like a bottom of a hill, where again your graph is changing from decreasing to increasing, turning from decreasing to increasing, that you have a minimum point on the graph. It also means that this parabola is concave up. Right, so concave up, another word we're going to throw in there, and I'll put that in just a minute. So vertices or minimums. Let's get a little ahead of myself with the concave up. Or if we look at the next picture, this one is changing from increasing till it gets there, then it turns at this point and turns to decreasing here. So again, when we change from increasing to decreasing or vice versa, we have a turning point. So this one is a minimum turning point. But over here, when we go from increasing to decreasing, so the reverse, again, we're still changing directions, we're still turning, but this one is going to be called a maximum turning point. And again, we have different types of maximums. We have the local or relative maximums, then we have the global or absolute maximums. We'll talk more about that later. So our turning points, again, changing from increasing or decreasing to vice versa. When it's the first, when we go from decreasing to increasing, that turning point represents a minimum. And when we go from increasing to decreasing, then that turning point represents a maximum. And those can also, again, be called vertices. So our turning points could be called vertices, and they could represent minimums or they could represent maximums in our graph. Okay, and they also, again, affect something called concavity. So that first parabola we say is a parabola that opens up, or to be a little more technical and use some of our math terminology, we say that that parabola is concave up. So we say this is concave up. The second parabola, where we're changing from increasing to decreasing, this parabola we say opens down. We also say it is concave down. And those are behaviors that not only can be seen with the increasing to decreasing change, but the actual concavity itself can change with what we call a point of inflection. So between an increasing and decreasing interval, we will see a piece of graph that is either concave up or concave down. But inflection points will actually change the behavior. We will change from concave up or concave down to concave down, or vice versa. So at a point of inflection, a function's concavity changes. And that's what I'm going to try to show you in this last one. So the concavity of this graph is changing. Now you might not see anything that's concave up or concave down because it's very easy to see with the parabola. Here, our point of inflection is this point right here. It's really the only point that looks more special than any of the others on that graph. So that is the point of inflection. I'm going to call it an inflection point, IP. Maybe I'll do this over here, IP, so that I don't have to clog up my picture. So at that point, again, my function's concavity is changing. So if I was to, here's how you can see it a little bit better. If I was to follow this parabola, you can go to pink here, follow this parabola, so we're increasing here, right? If I was to continue making the other half of the parabola, I can see how it would be a piece of parabola that is concave down. Or similarly here, I have this half of a parabola here. If I was to continue through that inflection point and make a parabola, then I could see that that portion of the parabola is concave up. So at that inflection point, we change from this piece is concave down to this piece is concave up. Okay, so again, not really easy to see on its own, but visualize that's half of a parabola. If you put the other half in, then you can clearly see how it's concave down. Again, I'm hoping that makes sense. And I'm hoping inflection point or a point of inflection is not a new word, but again, definitely something we're going to see a lot of in calculus. So we need to be able to identify end behaviors. This one's super, super important. And we need to be able to identify our turning points where we change from increasing to decreasing or vice versa, and our inflection points where our concavity is changing. So these last few concepts, which seem kind of simple, they're super, super big in calculus, okay? So hopefully you've got enough to get going on your homework, but as always, if you have any questions, please reach out, let me know. Until next time, take care.